often you have the situation that the Hamilton function is not explicitly time dependent. Typically whenever you have a closed mechanical system without external driving forces or varying external fields and so on, then you have a time-independent Hamilton function, and you immediately have a conservation law, namely that Hamilton function is then conserved, as a conserved quantity. If that is the case, then the Hamilton-Jacobi equation simplifies and gives rise to the time-independent Hamilton-Jacobi equation. Let me write this down for you. So if the Hamilton function h is not explicitly time-dependent, then we know that the Hamilton function is conserved, and it's a constant value E. I should remark, when the Hamilton function is time-independent, then it's a constant of the motion. And I gave that constant, I denoted that by the letter E, which seems to suggest that this is always the energy. And as a word of caution, the Hamilton function, as you know, is not automatically the energy. Additional conditions have to be satisfied so that the Hamilton function is indeed the physical energy. So even though it's suggestive, the constant E is not necessarily the physical energy. It just denotes the constant value of the Hamilton function. This implies that when we consider the partial derivative of the action function with respect to time, that was minus the Hamilton function, but in this case, this is then minus this conserved quantity, this constant E. But this equation, this differential equation, you can solve immediately. If you have this relation here for the partial derivative, then this immediately implies that the action function must be, you can integrate that equation, and this must be minus E times t plus something that doesn't depend on time anymore. That's a constant with respect to the time variable. So, and since the action function may depend on the q's and t, and that something, that additional constant here, must not depend on time, it can only depend on the q's. So there's going to be a term, and I call that W, which depends on the q's only and no longer on time. And this function here, this W, is called Hamilton's characteristic function. Now what happens when you have this expression here for the action function? What happens to the Hamilton-Jacobi equation? You can start from the first equation up there, namely the fact that the Hamilton function is conserved. So the Hamilton function is equal to this constant E, which usually is the physical energy, the mechanical energy, if the various assumptions are satisfied that we had discussed earlier. So that's our starting point. Still, the Hamilton function is a function on phase space, so it's a function of configuration Q and momentum. but momentum was the partial of the action function with respect to q. But here, the partial of the action with respect to q. When you look at the result up there, you express the action in terms of Hamilton's characteristic function minus e times t. You see the partial of s with respect to q is the same as the partial of w with respect to q. Right? And both of them give a little p. So we can use that in here, and instead of p, we can now write the partial of w, which is a function of the q's, with respect to little q. And the Hamiltonian, as we had assumed, doesn't depend explicitly on time, so there's no time argument here. This equation inside the box is now the time-independent Hamilton-Jacobi equation. And it's now a partial differential equation for the w, for Hamilton's characteristic function. And it has the great advantage that Hamilton's characteristic function is now a function of the q's only. It's no longer a function of time. We have eliminated the time dependence thanks to energy conservation. And when you can reduce the Hamilton-Jacobi equation to this time-independent form with Hamilton's characteristic function, then that simplifies significantly the solution of your problem. So this is a partial differential equation for W. Let's stick to the time-independent case, where we can write the action function S, as on the previous slide, as the Hamilton characteristic function W minus E times T. When we take the differential now, we might also, rather than keeping E fixed and allowing a variation of T, we might also say we keep the time, the final time T fixed, and allow a variation of E. So we say we keep T fixed, i.e. the final time, but instead we allow a variation of E. Then when we take the differential of the action function, then this is the W, the differential of the Hamilton characteristic function, minus the differential of E times T, but we say we keep T fixed and only E can vary. So we get a T times dE. What is ds? The differential of the action. The differential of the action we learned earlier. This is P dq final coordinates minus P dq initial coordinates minus Hamilton function dt. But we say we have no variation of time, we keep t fixed, and therefore dt is equal to 0. We can solve that now for the differential of the characteristic function, dw, we can say this equals pdq small letters minus pdq capital letters plus t dE. And this implies, in turn, that the time t, that must be the partial derivative of the characteristic function with respect to E at fixed initial and final configurations. And this is quite a useful identity, which we are going to use in the example. So this helps solve equation of motion, the equation of motion. So as an example, we look at a harmonic oscillator, and to keep things simple, we consider the harmonic oscillator in one dimension. The Hamilton function for the harmonic oscillator is given by kinetic energy, p squared over 2m, plus potential energy, and when we last considered the example, we discussed that the potential energy can be written as mass times omega squared over 2 times q squared. This is the Hamilton function for one dimension. It's clear this Hamilton function is time independent, so we can try to tackle this problem with the time independent Hamilton-Jacobi equation. In the time independent Hamilton-Jacobi equation, we have on the left hand side the Hamilton function, where we replace the momentum by the partial derivative of the w, the characteristic function, with respect to q. So on the left hand side we have 1 over 2m, and then instead of p squared we have the partial of w with respect to q squared. The potential energy remains unchanged, and on the right hand side we have E, we have the constant value of the Hamilton function. We can solve that for the partial of w with respect to q, and that gives us a square root, a big square root of 2m, and then the difference E minus m omega squared over 2 q squared. Now this is a differential equation for the characteristic function. It's separable, so you can integrate it, and if you like, you can get from that equation, you can get w of q. And then you have the characteristic function, and then you also have the action function, because that's just w minus e times t. And then you can proceed in this general way that I outlined before, that allows you to solve the equation of motion. So from here you can obtain w of q up to an integration constant, and then from there you proceed as outlined before. However, that's not the route I want to take, because there's an easier way to do it. And this easier way exploits the equation that we had on the previous page, where we consider E to be a variable. So this easier way is that now to this equation to this differential equation, we apply a partial derivative with respect to E. So we take both on the left and on the right hand side, we take a partial derivative with respect to E. The order of partial differentiation can be interchanged. So on the left-hand side, we can take the partial with respect to Q in front and pull the partial derivative with respect to E inside a bracket and say this is the partial of W with respect to E. And on the right-hand side, when we take the partial with respect to E, we find this is the square root of m over 2. And then we have 1 over square root E minus m omega squared half Q squared. Now this is something that we can, this is a differential equation that we can integrate in the Q variable. On the right hand side, this has, if you do a suitable substitution, you can reduce it to the standard integral 1 over square root of 1 minus x squared, and that standard integral is the arc sine, the arcus sine function. So after integration with a suitable substitution, you find on the left hand side you still have the partial derivative with respect to E, and on the right hand side you get 1 over omega, and then you have the arc sine of omega times square root m over 2e times q plus an undetermined integration constant. At this point you can use the equation that we found on the previous page. On the left hand side we have the partial of the characteristic function with respect to E, and we had shown on the previous page that this is equal to t. This is the time. That's final time t. So actually what we have here is an expression for t as a function of q. And now you simply have to invert this equation, solve it for q as a function of t, and you have the solution of your equation of motion. Yeah? So this is the last step. You solve for q, and you get q of t. This is then 1 over omega square root 2e over m, and then you get the sine of omega times t minus this undetermined constant. And you see that here you have a general solution. As expected, it contains two undetermined integration constants, namely E and C. These are our two integration constants. And they can be related then to the initial conditions of your system. So, of course, the harmonic oscillator can be solved in many ways, and you don't need Hamilton-Jacobi to solve the harmonic oscillator. Nevertheless, I hope that this example has convinced you, has shown that Hamilton-Jacobi has the potential of solving mechanical problems in a very elegant way. I mean, this solution here is certainly not more complicated than the standard solutions that you know. So as the last section of today, I'd like to tell you something about the so-called abbreviated action and the Maupertius principle. And it links to the time-independent Hamilton-Jacobi formalism that we had discussed. Let us consider extended phase space. So we have the phase space coordinates Q and P. We have, in addition, a time axis. Let's say here is time 0, and somewhere we have time t. Let us consider the case where the Hamilton function is not time dependent and therefore a constant of the motion, and therefore has a constant value along a physical trajectory. Let us pick one such value and say that value is E. So it's the letter we use to denote that constant value of the Hamilton function. And let us consider in phase space the set of all states where the Hamilton function has that value E. That will be some submanifold of, or subspace of phase space. It's one constraint. So the Hamilton function must have a fixed value. That's one constraint, and that will reduce the dimensionality by 1. So in here, when we have two-dimensional phase space, then the set of all states where the Hamilton function has a given fixed value will generally be a one-dimensional subspace. And generally it's one dimension less than the dimension of phase space. So let us say that in green here, this is the subspace in phase space, or the submanifold in phase space where the Hamilton function has this given fixed value E. Now I drew it here for the initial time t equals 0, but of course this applies to all times. So we can also extend that submanifold to all times, and then we get a submanifold in extended phase space. So this here is a submanifold on which the Hamilton function has the fixed value E. Now let's consider, as usual, a fixed initial configuration, and that fixed initial configuration is capital Q. Let's say that when we fixed the value of the Hamilton function, then this means that all physical trajectories must lie on the submanifold. So in particular, we must start at a point in phase space which satisfies both the initial condition for the configuration, so it's on this vertical line representing capital Q, that constraint, and it must also lie on the green submanifold. So there we have our initial condition. And then we have a physical trajectory here in red. That's our physical trajectory. And due to the conservation law, the physical trajectory must lie in this submanifold throughout. So the physical trajectory is constrained to the submanifold. The final state of that physical trajectory, the final state corresponds to time t, and it corresponds in configuration space. It has configuration q, little q of t. At this point, we go back to the concept of the action as a functional. So we say goodbye to the idea that action is a function of initial and final configuration. But now we go back to the idea of the functional, and we allow alternative trajectories, which are not physical, connecting the initial and final configuration. With the constraint, however, that the alternative trajectories must also all lie on the submanifold. So they must also satisfy the constraint for the Hamilton function, but for the rest they are free. So we can consider here alternative trajectories, and as we did when we considered the action principle, so we fix initial final configurations. Initial and final momenta are free, only the configurations are fixed. But here's an additional constraint. We require that the alternative trajectories too are constrained on the submanifold, constrained to the submanifold. And now we are wondering what happens to our action principle when we impose this additional constraint. So to that end, we consider our usual action functional S as a functional on trajectories in phase space, so pi of t, and defined as usual as the integral over time of the Lagrange function. But we restrict ourselves to trajectories constrained to the submanifold defined by Hamilton function must be equal to E. Now what happens then to the action functional? That's the integral over the Lagrange function, and we had seen earlier that we can write this L dt alternatively as P dq minus Hamilton function dt. L is p q dot minus Hamilton function, q dot is dq over dt. So multiplying this out, we get p dq minus h dt. But when we impose the constraint, we know the Hamilton function is a constant. That's E. So in other words, this is the integral p dq minus E times t. This integral here, integral p dq, that gets a letter that's w, like the characteristic function, but it shouldn't be confused with the characteristic function, because here we are talking functionals, not functions. So this is also a functional. It's a functional on the phase space trajectory, and it gets a subscript e, indicating that the trajectories are constrained to that submanifold characterized by e. And this quantity w subscript e, this is called the abbreviated action. And of course there is a relationship with the Hamilton characteristic function, because when you evaluate the abbreviated action on the physical trajectory, then you get the Hamilton characteristic function. You know that the physical trajectory is distinguished by the fact that it extremizes the action. That must also hold if we constrain the trajectories to the submanifold. So amongst all the trajectories on the submanifold, the physical trajectory must still be the one with the extremal action. But you see, the action is here given by the abbreviated action minus e times t. E is a constant, e is fixed throughout. It's the same for all trajectories that we are looking at. If in addition we also fix t, the final time, and that is usually done in the in this extremization principle, that you fix not only initial final configurations, but of course you fix also initial final times. So t is also fixed. So e times t, they don't vary at all when I look at different trajectories. So in fact, extremizing the action S is equivalent to extremizing W. So you can simplify your extremization condition if you have this time-independent Hamiltonian. You can focus on the abbreviated action. And so let me write this down. So for constant Hamilton function, the usual action principle is equivalent to the condition that the abbreviated action is extremized, and this condition is known historically as the Maupertius principle.